Namaste doston. Welcome back to our channel Sahi Hai. I'm Prajakta, and I'm super excited to dive into another fascinating topic in engineering mechanics with you guys, kinematics of particles. This is Unit 4, and trust me, it's a super important one. So, what exactly is kinematics of particles all about? In simple terms, it's like the Sherlock Holmes of mechanics, where we investigate the motion of particles without getting bogged down by the forces causing that motion. It's all about understanding how things move, their displacement, velocity, and acceleration. This might sound a bit abstract, but believe me, it's anything but boring. Kinematics is applicable everywhere around us. From a football soaring through the air to the graceful arc of a dancer's leap, it's the science behind the movement we witness every single day. Now you might be wondering, why should I care about how particles move? Well, for starters, if you're studying engineering mechanics, this is kinda essential stuff. But beyond that, understanding kinematics is crucial for designing everything from rockets launching into space to robots working in factories. Let's say you're designing a bridge. You need to understand how the bridge will behave under the weight of traffic, right? That's where kinematics comes in. By analyzing the motion of the bridge components, you can ensure it's strong enough to handle the load. Or think about designing a roller coaster. You wouldn't want your roller coaster to go flying off the tracks, would you? Kinematics helps engineers calculate the perfect speeds and angles to keep those thrills safe and enjoyable. So yeah, kinematics is pretty darn important. It's the foundation for understanding more complex topics in mechanics, and forms the basis for many real-world applications. Alright, so we've established that kinematics is all about motion. But before we jump into the nitty-gritty, let's take a step back and understand the different ways things can actually move. You see, motion isn't just about going from point A to point B. It can be simple or complex, fast or slow, straight or curved. And in kinematics, we like to categorize these different types of motion to make our lives a little easier. Think of it like sorting your clothes. You wouldn't just throw all your clothes into one giant pile, right? You'd separate your shirts from your pants, your socks from your sweaters. Similarly, in kinematics, we categorize motion to understand its unique characteristics and apply the right equations to analyze it. So let's start with the simplest type of motion, rectilinear motion. Imagine a car zooming down a straight highway or a cheetah sprinting across the savannah. That's rectilinear motion in action. In rectilinear motion, an object moves along a straight line. Think of a train chugging along a straight track or an elevator going up and down a building. The key here is that the motion is always along a straight path without any curves or deviations. Now don't mistake simple for boring. Rectilinear motion might seem basic, but it forms the foundation for understanding more complex types of motion. It's like learning your ABCs before you can write a novel. Mastering rectilinear motion is key to unlocking the secrets of kinematics. Section 3. Curvilinear motion. Alright, ready to add some curves to the mix? Let's talk about curvilinear motion. As the name suggests, this type of motion involves movement along a curved path. Think of a car navigating a winding road, a ball soaring through the air in a beautiful arc, or even the Earth orbiting the Sun. All these examples involve curvilinear motion because the path of the object is curved. Now, curvilinear motion can be a bit trickier to analyze than rectilinear motion because the direction of motion is constantly changing. But hey, that's what makes it exciting, right? It's like solving a puzzle. You need to break down the motion into its components to understand it fully. Section 4. Rotational motion. Last but not least, let's spin things around with rotational motion. This type of motion involves an object rotating around a fixed axis. Imagine the Earth spinning on its axis, a merry-go-round at a carnival, or even a simple spinning top. In all these cases, the object is rotating, and every point on the object moves in a circular path around the axis of rotation. Rotational motion is all around us, and it plays a crucial role in many mechanical systems, from car engines to wind turbines. Understanding rotational motion is essential for designing and analyzing these systems. Section 1. understanding projectile motion. Now let's talk about a specific type of motion that's a favorite in exams and real life. Projectile motion. You know, the classic scenario of a ball being thrown in the air or a cannon firing a shot across a battlefield? Yeah, that's projectile motion in action. In simple terms, projectile motion is the motion of an object that's been launched into the air and is only under the influence of gravity. So once that ball leaves your hand, or that cannonball blasts out of the cannon, gravity takes over and dictates its path. It's like a graceful dance between inertia, the object wanting to keep moving in a straight line, and gravity pulling it back down to Earth. Now you might think projectile motion is just about things going up and down. But here's the interesting part. The object actually follows a curved path, specifically a parabola. That's why those cannonballs don't just go straight up and then fall straight back down. They travel horizontally as well, creating that beautiful arc we associate with projectile motion. Section 2. Key concepts and formulas. To really get a handle on projectile motion, we need to understand some key concepts. First up, we have the initial velocity, which is the speed and direction at which the object is launched. This initial velocity can be broken down into two components: horizontal velocity and vertical velocity. Then we have the angle of projection, which is the angle at which the object is launched with respect to the horizontal. This angle plays a crucial role in determining the shape of the parabolic path and how far the object will travel. And of course, we can't forget about gravity. The acceleration due to gravity is a constant force pulling the object downwards, causing the vertical component of velocity to change over time. Now, I know what you're thinking, formulas. Don't worry, we'll get to those. But before we start crunching numbers, it's important to understand the concepts first. Once you get a feel for how projectile motion works, the formulas will make much more sense. Section 3. Breaking down the motion. So, let's break down the motion of our projectile into two parts, horizontal and vertical. In the horizontal direction, there's no acceleration, assuming we're ignoring air resistance, which we usually do to keep things simple. This means the object will keep moving at a constant horizontal velocity throughout its flight. But in the vertical direction, gravity comes into play. The object's vertical velocity will change due to the constant downward acceleration. As the object goes up, gravity slows it down until it momentarily stops at the highest point of its trajectory. Then, as it falls back down, gravity speeds it up again. Now, here's the cool part. The horizontal and vertical motions are independent of each other. That means we can analyze them separately and then combine the results to get a complete picture of the projectile's motion. And that's where those handy-dandy formulas come in. By using the equations of motion and our understanding of the horizontal and vertical components, we can calculate all sorts of things about the projectile's flight, like how far it will travel, range, how long it will stay in the air, time of flight, and how high it will go, maximum height. Section 1. Motion under gravity. Alright, so we've talked about projectile motion, which is a special case of motion under gravity. But gravity affects everything, right? From a tiny apple falling from a tree to a giant rocket launching into space, gravity is the invisible force that shapes our universe. In the simplest terms, motion under gravity means an object is moving freely under the influence of gravity, with no other forces, like air resistance, messing things up too much. It's like a solo dance between the object and Earth's gravitational pull. Now, here's the cool part. When an object is in free fall, its acceleration is constant, and it's equal to the acceleration due to gravity, which we usually denote by g. This little g is a superstar in physics, and it has a value of approximately 9.8 meters per second squared on Earth. Section 2. Introduction to relative motion. So far, we've been talking about motion from a fixed point of view, like we're standing still on the ground and observing the world around us. But what happens when things start moving relative to each other? That's where relative motion comes in, and it can get pretty interesting. Imagine you're sitting in a moving train, and you see another train passing by in the opposite direction. From your perspective, the other train seems to be zooming past at super speed. But someone standing on the ground would see both trains moving at their respective speeds. That's relative motion. The perceived motion of an object depends on the observer's frame of reference. In simpler words, relative motion is all about understanding how the motion of one object appears from the perspective of another object that might also be in motion. It's like a game of cosmic tag, where everyone's chasing each other through space and time. Section 3. Relative motion, ship, and boat scenario. Let's dive into a classic example of relative motion that often pops up in exams, the ship and boat scenario. Picture this. You're on a big ship sailing smoothly across the ocean, and you spot a small boat bobbing up and down in the distance. Now the ship has its own velocity. Let's say it's moving eastward at a certain speed, and the boat might also be moving, maybe northward at a different speed. So how do we figure out the boat's velocity relative to the ship, or vice versa? That's where vector addition comes in handy. We can represent the ship's velocity and the boat's velocity as vectors, with both magnitude, speed, and direction. Then by adding these vectors using the rules of vector addition, we can find the relative velocity between the ship and the boat. It's like solving a puzzle, but instead of fitting pieces together, we're combining velocities. This concept helps us understand how the boat appears to move from the ship's perspective, which is crucial for navigation and avoiding collisions at sea. Section 1. Defining velocity. So far, we've been throwing around terms like velocity and acceleration, but let's take a moment to really understand what they mean. First up, velocity. You probably use this word all the time, like, hey, that car is going at a crazy velocity. But in physics, velocity has a very specific meaning. Velocity is basically the rate at which an object changes its position. It tells you how fast an object is moving and in what direction. It's not enough to just say, that cheetah is fast. We want to know how fast, like 100 kilometers per hour fast. And we also need to know the direction. Is it running north, south, east, or west? Velocity is what we call a vector quantity, which means it has both magnitude, the speed, and direction. We represent velocity using arrows, where the length of the arrow shows the speed, longer arrow, faster speed, and the direction of the arrow shows, well, the direction. Now let's talk about acceleration. Acceleration is often misunderstood as just speeding up, but it's actually a bit more nuanced than that. Acceleration is the rate at which an object's velocity changes over time. Think about it this way. If you're driving a car and you slam on the gas pedal, your car accelerates. It speeds up. But if you slam on the brakes, your car also accelerates. This time, it slows down. And if you turn the steering wheel, your car is still accelerating, even if your speed stays the same. Why? Because you're changing the direction of the velocity. And remember, acceleration is all about changes in velocity. Just like velocity, acceleration is also a vector quantity. It has both magnitude, which is how much the velocity is changing, and direction, which is the direction of the change in velocity. Now let's talk about time, the unsung hero of motion. Time is what connects velocity and acceleration. It's the glue that holds everything together. See, velocity is all about how an object's position changes over time, and acceleration is all about how an object's velocity changes over time. Time is the common thread that links these concepts together. Think of it like a road trip. Velocity is like your speed at any given moment. Are you cruising at a steady 60 kilometers per hour or zooming along at 100 kilometers per hour? Acceleration is like how quickly your speed changes. Are you gently accelerating to pass a truck or slamming on the brakes to avoid a squirrel? And time is like the duration of your trip. How long did it take you to get from point A to point B? All right, folks, get ready to unleash the power of equations. We've talked about the concepts of horizontal range, time of flight, and maximum height in projectile motion. Now, let's translate those concepts into some handy-dandy formulas that'll make solving problems a breeze. First up, horizontal range. This is the total horizontal distance covered by our projectile during its flight. The formula for horizontal range, R, is R equals u squared times sine of 2 theta divided by g, where u is the initial velocity of the projectile, theta is the angle of projection, and g is the acceleration due to gravity. Next, we have time of flight, which is the total time our projectile spends in the air before returning to the same vertical level. The formula for time of flight, t, is t equals 2 times u times sine of theta divided by g, and last but not least, maximum height. This is the highest point our projectile reaches during its flight. The formula for maximum height, h, is h equals u squared times sine e squared of theta divided by 2 times g. Now, I know staring at formulas can be a bit intimidating, like trying to decipher ancient hieroglyphics. But trust me, these formulas are our friends. They're like cheat codes for solving projectile motion problems. Let's say you're given a problem where you know the initial velocity of a projectile, the angle at which it's launched, and you need to find out how far it will travel horizontally. Boom! Just plug those values into the horizontal range formula, and you're good to go. Or maybe you need to figure out how long a ball will stay in the air if it's kicked at a certain angle and speed. No problem. The time of flight formula is here to save the day. And if you want to know how high that rocket will soar into the sky, the maximum height formula has got your back. Remember, these formulas are like tools in your problem-solving toolkit. The key is to understand what each variable represents and to choose the right formula for the job. And with a little practice, you'll be solving projectile motion problems like a pro. So, there you have it, kinematics of particles. We've covered a lot of ground from the different types of motion to projectile motion, relative motion, and those all-important formulas. I hope you guys feel more confident about tackling this topic now. Remember, kinematics is all about understanding how things move. It's like being a detective of motion, analyzing the world around us with the power of physics. And the best way to master this topic is to practice, practice, practice. Don't be afraid to get your hands dirty with numerical problems. Work through examples, try different scenarios, and don't give up if you get stuck. Remember, every mistake is a learning opportunity in disguise. And hey, if you ever need a refresher, just come back to this video. We'll be here, ready to break down those concepts and help you ace those exams. So go out there, embrace the world of motion, and remember, Baki Sab Sahi Hai. Don't forget to like, share, and subscribe to our channel for more awesome engineering mechanics content. Until next time, keep those brains buzzing and those curiosity gears turning.